Welcome to another GCBASIC demonstration. This is part 15 for the PIC18FxxQ20 chip family, and this is specifically looking at interrupts. If you'd like and subscribe this video, please. So like the video, subscribe to my channel, and let it run all the way through. Thank you. So we're looking at an external interrupt in this particular one, but I'm going to introduce the concepts of interrupts in the round, but we're going to control an LED. Okay, and you can adapt this into changing the sequence of LEDs or whatever. So, principles of interrupts. These are events that happen that halt the normal execution of your program. It allows you to respond to specific events, and that event list is predetermined by microchip, and we'll have a look at those predetermined events. And it allows you to actually have some great advantage. You can respond to a critical event that's outside the normal flow of your program, and it really makes it very efficient for a microcontroller. You can have external events, timer events, peripheral, software, a whole list of things. And we'll look at a full list in a moment. There are some key registers, but a lot of those registers are all controlled by GCBASIC. And from a GCBASIC standpoint, we don't actually have to have a look at them. We will look at some assembly today just to say and convince people it's working. And then there is a special function called an interrupt service routine, the fourth thing on that major bullet there. It's a special function that executes when the interrupt occurs. Keep it must be very short and efficient. So avoid big delays in there. Just get the job done and get out, because you're stopping the operation of the major program, the major part of your program. Here is 65 interrupts for this particular chip. Earlier chips had 8, and this covers timers, it covers DMA, communication protocols, many of those in the internal and the external interrupts. What we're going to do is I've chosen one, and it's called port A B change. And what these little flags mean is that when that event occurs, to make it happen, you must have set a flag called IOC, IE, which is interrupt on change, interrupt enable. IOC, IE, interrupt on change, enable. And then it sets a flag when it actually happens. When something in that class of events happens, it sets a little flag to say I've happened. And you can test against that. And you can test against IOC, IF to say the interrupt flag has occurred. And you can test and go, whoa, something's happened. And then once that flag's happened, you can go after your little routine that you've written. So it's quite clever. Slightly different in the AVR chips, but this is the way it works here. So key points. We're going to look at interrupt on change. That's detecting change on the state of change on a specific pin. So we need to set up the IO pin as an input. We need to set up the correct register for the edge detection, either rising or falling, could be both. You need to set up the ISR, interrupt service routine, and then the global interrupt will be handled automatically. Well, sounds all very complex, but let's look at it, how we do it in GCBASIC. Well, one good thing is that we just need to check I look in the data sheet. I looked at RA3. I looked at the column in here in red column IOC, and I can see that IOC A3 is a valid interrupt on change port. This particular chip, every port can raise an interrupt on change interrupt. That is not the case on all PICs and LGTs and AVRs. So you do need to check that it's valid. Normally, look at the row, and then look at the IOC column, and where is an intersection? If there's a name in there, you're okay. So what's the code look like? Well, let's just bring up a pointer. Pretty simple. We need to set up an interrupt on change pin, and I've set it up going negative. And when that goes negative, the bit will be set, a bit will be set, and it will call the interrupt. And that's here. That's this piece of code here. In GCBASIC, you just use this command and instruction set to call the interrupt handler. You go on interrupt, whatever the source of the interrupt is. We've done port change. Call my interrupt handler. And you could call that whatever you like, but it has to be a subroutine that handles your interrupt. And I've called it interrupt handler to keep things simple. And here is my handler. So this will run all the time. Every time there's an interrupt on the port change, it will come into here. Pretty cool. And I've just quick program. I said define a bit, save the switch state because I'm actually going to use the switch to detect it. I'm going to toggle the LED, wait until the switch state has changed, and then I have to set this specific flag to say that I am clearing the IOC A3 flag, and it's called IOC AF3, which is the flag for port A3. And there'll be others, there'll be many others, and we can look at that if we have time. But the rest of it is all cleared by GCBASIC. Everything else is handled automatically. So let's walk the example and see what we've got. So first of all, we're going to look at desk cam. Oh look! Oh, I must have whacked the camera at some point this morning. I've got an oscilloscope. You can see that's doing some pulse width modulation left over from previous video. I've got a switch here. If I push it, nothing happens because I've got no interrupt. And when I push this, in a moment, magic's going to happen. But that's what we're looking at. Here's the program. Very simple. All this stuff at the top we've seen before. Set up the chip, option explicit. Clear the PPS out because we want to make sure that we've got nothing laid over from previous. And I've got a switch on port A3 here. Port A3 has my switch, and I have an LED on there. I have 4 other LEDs, but I'm only looking at that particular one today. The rest of this sets up the ports as outputs. And here is the whole of the program we were just looking at. And it says here, set up the on-change bit, associated bit, that says A3 goes negative, and that just turns it on. The 1 turns it on. Here's the handler on interrupt port change, call our handler, and here is the code again. Sets a bit, creates a bit, caches the state of the switch as it comes into the routine, toggles the LED, waits for you to change the state of the switch, and then clears that flag, and you must clear that flag. Otherwise, it would always be set, and it would only go in once. I've just pressed function key F5, hex and compile. Well, we know that the scope will stop because we've just reprogrammed the chip. Look, as I push it, the LED flashes. And you can see it on the scope, it goes high or low. And I'm toggling it. And obviously, if you didn't want to toggle it, you wanted to do something else like pulse it for some period of time, you could do that as well. But keep the operations sweet and short. No. Now, what I will do is I'm just going to show you if I just take out that clearing of that flag. If I don't clear the flag, the handler will come in. It will come into the handler, the microcontroller, and that flag will always be set. And therefore, the event will never re-happen. It only happens the once. He said, "Huh, well, that didn't work out as I expected it to be. But that must get cleared automatically." Some of them do get cleared automatically. So this must be a clear automatic. But here we go. That's the interrupt. Now let me look at the assembler just to show you what's going on in the back end of this machine. So in here, we're going to look at some assembler. It says in here that we're going to, when the program starts at at the base level at address 0, that's where the program jumps to normally. It's called BAS program start and into the assembler. But when there's an interrupt, this particular chip goes, okay, I need to branch to something called interrupt. This is added automatically. But also note, somewhere in the program is because you've created an interrupt routine and you've used the onInterrupt command, it's also adding enabling global interrupts. And if we cursor down, here is the interrupt. It says, okay, somewhere in your program you've used 2 system variables or 1 system variable. It automatically caches that away. It then says, okay, has an interrupt occurred based upon our enabled bit? Is it the one that we are looking for? If it is, then it goes to our interrupt handler. Oh, then it clears it. And that's where I didn't know that because it happens automatically. It clears it, and then it restores the variables, and it returns back to the program. And so it's in the routine and out. It's as fast as that. And you might go, no, it's not doing it like that. Well, if I just go back to the program, and I'm just going to go into our loop program here and go LED D6, which is the one that's next to it. So now I'm going to turn on, I think it's the green LED. It's just going to flash all the time. There we go, you can see it flashing. That's really good. I pushed the button and it doesn't look like anything actually happened. Oh, of course, the way I've written it, it will wait until I've changed the state of the button up. Bad code. Oh, that's a really piece of bad, nasty code because it's getting stuck in a loop here. Nasty, nasty. That's why you need to be very careful in interrupts. I would not do that then. I would take that out, say testing, and go for it. Just going to reprogram it. You can see that LED 6 is now flashing. That's better. I was being over ambitious with the debounce. So you need to add a proper debounce into there. That's working fine now. That's excellent. So whilst we're here, I just wanted to show you something else on interrupts as well. So that was demonstration 250. 251 is really also using an interrupt. This interrupt, let's have a look what the interrupt is. It says on here, what's the interrupt? Oh, look at this, look. Timer overflow. So this one is going to generate a pulse width modulation signal in the interrupt. Okay, so we'll just go through this and see it working. So this is pulse width modulation 7th way, because in the previous video I said there were 7. This is one of the 7th ways using an overflow. So how does this work? Well, basically we call all the headers the same, set up some variables, define and it's really for motor control, this one. So I'm using the LED to represent my motor. In the motor control, what's in there? Look, it says in here, set some variables up, but it sets up a call to the timer 0 overflow. So whenever that equals 0, it will call something called PMW handler. I set up the timer with some with the prescaler, clock source, and a post scaler. And all I'm doing is setting those to 1, so it's just free running. It's free running, and the clock is free running, and every so many seconds or milliseconds, it will call this particular routine. And you can change this to get it faster or slower. And in here, this is my handler. It says turn the motor on or off depending on whether a counter called PMW counter is greater than 100. And so it's just going through and says, right, if the motor speed, which is a value that I'm sort of controlling, if it's greater than that, turn it on or off. And if you look in here, it's extremely simple. It says the speed of this is 0 to 100, and that will then decrease the power on this motor over 2.5 seconds. But what we're taking away from here is not the motor control, it's the fact that we're calling another interrupt called timer overflow, and this one is generating a pulse width modulation signal. And you can see that on the scope and on the LED. With that, we're going to call it a day, call it a job done. Next time we will be looking at using storage within this PIC. We're going to look at progmem, SAF memory, EEPROM and data blocks. Just a way of creating lots of data inside of the microcontroller. After that, we'll drop out the back end with CLC, last technical one, and then we'll just do reviews and get out of here. With that, call that a wrap.